Cool. So welcome. I am Lindsay. I will be covering for Ish today, project office hours. Thank you so much to everyone who put in questions. I can see a couple of y'all are in here. It looked like two people put in a series of questions. So yeah, would y'all like me to get started on those? Or does anyone have any quick questions that they want to just like throw out there real fast? All right. This is like an intimidating wall of names and a couple of pictures in terms of like talking to for office hours. But I guess I appreciate that. I can certainly go through and start to answer some questions step by step. One thing that maybe I'll do is start with some of the more conceptual questions that I saw that were on the Slack thread. See if that leads anywhere. And then I do have a notebook open, but let's just start off with some of the more conceptual questions that I saw. Yeah, so Mark had asked if I'm using something like forward or backwards stepwise selection of features, does that risk overtraining the data? Yes. So anytime that you're doing anything on your data, especially feature selection and feature engineering, you're going to want to always evaluate it on a test set. So one of the very first things that I like to do when I open up is I'll create the test set that I'm working on in for a project at the very beginning before I do like literally anything else, even sometimes before I go into any kind of exploration, because the whole point of separating out a test set is this idea that you want any work that you're doing to be generalizable. What does that mean? So like, if you think through how you're going to use your results, the idea isn't that you just want to do this one time. You'll want to potentially do this in the future. So in the context of this project, like, it's not that I want to predict these sale prices. If I just wanted to predict these sale prices, I already have them. Like, that's okay, cool. But I'll want to additionally do stuff like if I have a new house that goes on the market, it hasn't sold yet, can I predict what that sale price actually is going to be? How will I know if my model generalizes well to unseen data? Well, that's the point of a test set. And so before I do anything else, typically I'll go through and make that test set so that I can really make sure that it is truly acting as unseen data for the purposes of my model. The more you can remove the test set from your analysis, the better, because that way you can really have a good gut understanding of whether or not it's going to work when you try to do it on new data that you don't have the right answer for. So in terms of forward and backward selection of features, the best way to make sure that you're not overfitting to the training data, which absolutely that stepwise selection of features has a very strong tendency to overfit if you don't evaluate on a test set. And certainly you can look at something like the significance level from a scikit-learn, not scikit-learn, from a stats models perspective or something like that. But in the end, I think the best and easiest way to make sure that your model is going to do well for an unseen, for the future work is going to be to do like test it on your test set and be like, okay, well, how good did I do? Did I do like get a good accuracy score or a good root mean squared error on future work? Then probably I haven't overfit to that training data if it does well on the test set. Of course, there's all kinds of things of like, is your test set really going to generalize well? That's a whole different set of issues. But that's kind of the conceptual answer to the first part of that question. We'll talk about doing it directly in code later. But I did want to talk about conceptual questions first. And welcome to everyone who joined in the last couple of minutes. I did already get started, but as you all can see, I am recording this and I will put this live and put up everything at the end of the session. So my goal was to go through all of the conceptual questions that people posted, and at any point turn on your cameras, interrupt me, to chat. Like, I would like to make this as open and interactive as we can. But I will go through and talk through conceptually again, k-fold cross-validation. Why? Like, what is it? Why is it there? I just went through and was talking about all this stuff with like training and test set. Like, what is this other piece with this k-fold stuff? What is cross-validation? Well, one thing that I mentioned is like, how do you know if your test set does a good job of basically pretending to be future, like unseen data, right? End goal is to be able to run a model that eventually will work on data that you don't have the right answer for. And so how do I know if that works? I evaluate on some data the model hasn't seen yet. Well, k-fold cross-validation basically takes the idea of saying, okay, well, I'm not going to judge anyone's masks A+ for getting a mask, or wearing one rather. Yeah, so k-fold cross-validation says, okay, one test set is great. What happens if we do 3 of them, or 5, or 10? That's all k-fold cross-validation is it basically separates your data into training and testing sets, but it does it multiple times so that at some point, each row in your data is always going to be part of your test set, so that you never have a, like let's say that you accidentally have, just by random chance, you have a test set that really doesn't represent most of the data your model will see later. That you always have that chance, but if you do something where you're testing and letting every single row at different points be part of your test set, then you can basically say, okay, as long as my data in general generalizes well to future unseen data, I don't have to worry about the test set, that train test split itself being a bad representation. It also helps you prevent overfitting to just that train set. Because what you're doing is basically breaking up your model 5 times. Typically, everyone talks about 5-fold cross-validation, although you can do as many folds as you want. Certainly, depending on the size of your data, 3 might be enough. I've seen people do 10, but what you're going to do, right, is you're going to go through and say, okay, I'm going to do this 5 times, right? If you have 5 different train test splits, you're going to train 5 different models. And then how do you bring these things back together? Well, in terms of evaluation, what you'll do is you'll actually say, okay, I'm going to look at my scores on the test set for each of these ones. And then I'm going to look not only at the average one of those test scores, but plus and minus the standard deviation. If I've got a really small standard deviation between my test scores across all 5 folds, what that means is that it performed about the same way on all 5 of those test sets, which means that I don't have a wildly different test set each time. My model in general does pretty well. And so when I'm evaluating something that's done 5-fold cross-validation, I'm not only looking for a high score, but I'm looking for a tight standard deviation across those scores to make sure that it's not doing really, really well when I have a certain split in my model or in my data, but really, really badly when I have a different split, because that means my model probably doesn't generalize well. So that's the point of cross-fold validation. Anytime that you use a train test split, you can use cross-validation instead, basically. You don't necessarily need to do both, although one thing that you will see is that people talk about a validation or holdout set. This is another additional set. So not only do you have your 5-fold and you could have a train test split, you can do the same thing. This would be the very beginning, before ever looking at your data, randomly sampling a very small amount and just pretending it doesn't exist until you're totally done with everything in your process. You are about to deploy this model into the wild. This is the last holdout that you test on right before that deployment. And if it does noticeably worse than it has done at any other time, that you maybe slow your roll. You're like, okay, I'm going to pump the brakes on this one. I'm going to actually Like I thought I had gotten to the point where I had a really good generalizable model. I bring in this holdout set that I'd separated at the very beginning. I haven't even looked at, haven't even touched, and it does terribly, way noticeably worse than everything else. Like, oh, shoot. Time to go back to the drawing board because clearly something's gone wrong in this process. We don't typically require that you do any kind of holdout set, but you will see that if you look at things like Kaggle competitions or other places where people do data science. They'll talk about, and the, I'm so sorry, everyone uses different language for these things. Some people talk about that as their final test set, and they talk about a validation set that they use throughout. Like, so people interchange this language all the time. Just, I think, despite other people or people that are new to the field, I don't know why, like there's not more consistent language, but like, for example, quite often you will find in Kaggle competitions or like Kaggle data sets that they'll like give you data sets and they have different labels on them. And sometimes they use validation as like the test set instead of test. I don't know. Typically though, you can just talk about a training data, the data your model gets to see and learn from, the testing data that you're using to evaluate how it does as you go through the process and iterate, and then a holdout set at the end that you're only testing on once. So that is a high-level overview of K-fold cross-validation. In terms, again, of the actual implementation, I wanted to do conceptual stuff first. So I just talked for a while about different aspects of things that could potentially overfit, as well as like selecting features and cross-validate. Like, who's got questions for me? Who was like, oh my goodness, Lindsay is so different from Ish. Like she would talk so much slower or explain this so much better, but Lindsay is going through and just like steamrolling at you. Like I have a completely different style from her, which is always great when I get to cover for her. But cool. No questions so far. Like I said, interrupt me at any point ever, really.
Do you have access to that Google Doc where we were writing questions?
No. What Google document?
It's on our course repo or on our homeroom. There was a link to that. I don't know if you have access to that. Oh,
I don't know that I have access to your homeroom page, in fact. Let me actually see.
Or I think in the chat, somebody just put a link to it.
You guys are great. Okay, let me go find it then.
Because there might be some questions in there.
Sweet. Thank you, by the way, Melody, for yes. Sorry that there was confusion about the links there. I don't see a Google document. Am I blind? I did see some people had posted in a thread with questions, and those are the ones where I got started.
If you look in the chat for Zoom right now.
Oh, sorry, I'm looking in your Slack. Thank you guys. Cool. So questions. I'm guessing the ones that have red next to them are answers.
Correct.
Cool. So I see one at the very top, which is a great one that actually blends right into what we've just been talking about. And it's fine that you guys are quiet, but thank you for pointing these things out. Because yeah, I definitely want to answer as many questions as I can in these office hours. But the very top question that I'm seeing on this Google Doc says, when do we update our test set to match the transformations we did on our train set? Does the test set need to have the same transformations applied before predicting? Yes. So the good thing about scikit-learn is it does all of this stuff for you. Scikit-learn is really good about this, and that's why you have both a fit and transform. So fitting is always going to be the process where you're learning something from the data. Anytime you see fit in scikit-learn, what that means is I am going to learn the patterns, and the fit itself just learns the patterns. It doesn't do anything, and you have to do the transform to apply them. But let's say you've got a train and test set and you're doing something like scaling your data. For any linear model, it is always good practice to scale your data because your data is not smart enough to realize that things are on different scales and that those scales don't mean that they're of different levels of importance. It's just seeing numbers. And it's like, oh, this big number's got to be super great and important. Not necessarily always, but that's what it's going to think. And so you'll have trouble with feature selection, especially using some like techniques of feature selection and like feature importance if you don't scale your data beforehand. Plus, just an easy thing to do. So let's say you've got some kind of scalar. Well, the thing about that scalar is it's learning something from your data. And anytime it's learning something from your data, you want to make sure it's only seeing the data that you're thinking it needs to train. So, because you could imagine, for example, you've got a column with all of your square feet, total square footage for the house. And you've got something where you're going to want to scale that data down so that you can also put them in other things that are on a scale from 0 to 1. So you might look through lots of different scalars on scikit-learn, but maybe I look through and decide that a robust scalar is the best option. This applies for across all scalars, whichever scalar you end up using. Standard scalar is the one where it actually takes the mean and standard deviation, lots of different scaling options in scikit-learn. So choose whichever one feels right. We can talk about the different reasons you would choose different scalars if you want. But for the purposes of talking about transformations, and let's actually keep with the standard scalar for this, because I think that that's going to be the easiest one. So let's say you've got a standard scalar that you're going to apply. If I do it on my whole data before a train test split, my scalar is going to look at the average based on the whole data, the whole column, every single row that I have. And if I do it after a train test split, it's only going to take the average for the data that's in the training data. So you can see how that mean is going to be different, and you can see how that standard deviation is going to be different. The ranges of data potentially, right? What if your maximum value, the biggest possible square foot, ends up being in your test set? And that potentially, maybe it's not a true outlier, but it's on the far edge, right? It's your maximum value. If that's not in your training data, then it's not going to have as extreme of a mean, right? Mean is very much affected by things on the end. And so what the mean that it finds in that standard scalar is going to change whether you do it on your full data set or you do it on a train set. Anytime that you have a transformation that is going to be impacted by the data itself, you only want to do it on the training data, because the test data is supposed to mimic data your model has never seen before. You are saying by applying a train set that it should be able to learn everything it needs to know from this train set. And if it doesn't, I want to know about it. Like if it can't learn all of the proper patterns from the training data, then it means that my training data isn't good enough to predict into the future, to basically keep using this and actually turn this into a model where if I have a new house that comes up on the market, I should be able to apply the scalar to the square footage stuff and predict the sale price accurately, even though I don't know the sale price yet because it hasn't sold. So I want to be able to generalize into the future. So all of these transformations learned from something should be done on the test set or train set, not including the test set. And so you do a fit transform on the training data, just a transform by itself on the testing data. And that transform you can apply on anything. You can have a brand new thing come in and you could basically send it through and say, okay, so let's say I've got a brand new house. I don't know the right answer yet. I'm going to go through and transform this column using this transformer. I'm going to transform this thing using this transformer. Maybe I'm going to encode some variable. So I've got some categorical columns. But what happens if I have something where like I did a one-hot encode? So I got those dummy variables out, but it didn't ever see that before. Right? When you take a column and one-hot encode it, you turn each unique value in that column into its own column. and just turn it into a binary indicator that says, is it this? No. Is it this? Maybe, etc. If you have an option that comes in your testing data that it never saw in the training data, it's not going to get, it's going to have all zeros across all of those one hot encoded columns. And that's okay. That happens. It happens quite a lot, for example, when you start getting into things like natural language processing and you're dealing with all of those columns are one hot encoded or different kinds of indicators based on the words that it sees. Like this happens quite often all the time, that you get data that doesn't perfectly mimic what happens in the real world. And so like if you have a new zip code that you put in and you one hot encoded all of your zip code columns, well, maybe it's just got zeros all the way across. And you want to know how your data is going to deal with that. You want to know if your model is still going to give you an accurate answer. So yes, all of those kinds of transformations. You train on your training data and then transform your test set. And you can do that transformation as soon as you've trained.
Excuse me.
You're doing. Yes.
Before train test split, we should address the multicollinearity between these columns because it will change all of our data features.
Yes. Whether you explore multicollinearity before or after or both. So one thing that would be interesting is actually doing it both times, because what you'd think is that a column that exhibits strong multicollinearity between other columns before your train test split should still be strongly multicollinear after your train test split. You can think of that as part of the data exploration process before you actually do that split. I think I'm a little bit paranoid. I do very little exploration on my test data. I always do most of that stuff on my training data. That is not necessarily what everyone does, and it doesn't necessarily that's more me being paranoid than it is like perfect standard practice. But it's all about, right, getting an understanding of what your model is going to see. What happens with multicollinearity is that your model has no idea whether column A or column B drives this process. It can't distinguish them because it sees that they're both moving together. It has no idea which one is actually in charge. And so it maybe says, okay, I've got these two columns that are super multicollinear. Like, I'm just going to take everything from column B, but maybe it's a little bit of column A that actually is driving this. But I'm not going to see that because my model is just going to check what the whichever one it decides is like driving this process. And so dealing with multicollinearity, I don't think it really makes an impact long term, whether you do it before or after, because you should see those same patterns before and after a train test split. Like it should be pretty consistent across your data. If you're seeing a strong enough multicollinearity that you need to address it, then like you should see it across your whole data and in your training data. Personally, my philosophy is to do anything where you're making decisions only on your training data. Does that help?
Yes, thank you. And the same thing happened for categorical data. For example, at the end of the projects, we might want to change our categorical data.
What do you mean?
Example, in this project, zip code.
Mm-hmm.
We can categorize zip code based on geographical location or their unique values. I don't know what's the difference between these.
Yeah, so the thing about categoricals is it's always kind of tricksy. Because what happens here, and it's a good catch, right? Zip code looks like it's a numeric column. It's not really, right? My zip code is not one more than the zip code before it and one less than the zip code after it. Like you can't treat them like numbers because then it's going to understand a relationship between these zip codes that doesn't exist. So everything dealing with categorical variables is all about how do I get my model to understand the relationships that I know to be in there. Zip code, I know to be something that actually conveys something about a location. So encoding it based on location could be a really good way to address it. You could also do something where you showcase that these are completely separate things by one-hot encoding. Those aren't the only be all end all, right? Like there's plenty of different ways to turn a categorical variable into a number. And that's all it is, right? You're just basically saying, my model only understands numbers. How can I tell it a number that helps my model understand the relationships that I know to exist? How can I convey my understanding to my model? And so, for example, you could do like, we only really talk about one-hot encoding because in practice, that is very often what is used. But there's lots of other ways where you could do something like, what if I do the frequency of my training data? How often this shows up in my training data? And that will convey basically a sense of like the concentration of it. If I think that that is an important part that I want my model to understand, then I'm going to say, okay, frequency encoding this is going to give it a sense of like how often something shows up. And so now all of a sudden, rather than having these individual zip codes that don't really connect to each other numerically, I'm going to have it as a frequency of how often this showed up in my training data. So it says, okay, this zip code, I have your like the data behind you guys. So let's say 98077 is the most common zip code in my data, and it shows up 33% of the time. Well, now 33% is the number that I tell my model, as opposed to what 98077. And that number means something and connected to a zip code that only shows up 15% of the time or 5%. Like that relationship now matters. That could be a way to encode variables. And so how you encode your variables and what actually ends up working well in your model is something you're going to have to play around with. Maybe you try one-hot encoding and you get good results. Cool. That's great. Stick with it. But maybe you try one-hot encoding and you now have added too many columns to your data and your data ends up being really overfit. A feature of having quite a lot of columns in your model, in your data, is that the more columns you add, the easier it is for your model to overfit, because you have to think of this in like your model is finding some line that really is this like crazy hyperplane in space between all of these like features, right? All of these X variables. And so that finds it is easier to slice and dice and like find exactly what the line can be to match your training data if you give it more dimensions to do so on. Sorry, but deep into the weird linear algebra behind some of this stuff for a second there. But that is the curse of dimensionality. The more dimensions you give it, the more likely it is to overfit. So if you one-hot encode and you have all of these dummy columns and you find that your data is really overfit, you'd be like, oh, well, it's probably because I just added 30 columns to my data. Let's try something else. Let's do some other way of encoding the data. And that's just a process. It's just an iterative process where you say, okay, I'm going to make a single change, a different encoding technique. I'm going to apply, like learn the pattern from my training data, apply it to my testing data, and evaluate. Did it get better or worse? And then think about why. Why did it get better? Why did it get worse? Do I trust this? Me questioning my models every time I run them of like, do I actually trust what you're telling me right now? Like, that's something that I think comes a little bit more in time, but like, you know, sometimes something will get better, but maybe it shouldn't have. Maybe it's getting better for all the wrong reasons, but that's something where I think we build up to the more and more comfortable you get with machine learning. But I think in general, just thinking through, did this make an improvement? Does that improvement make sense? Or did this get worse? Does that make sense? Well, yeah, I just added 30 columns to this and now it's really overfit where I have a really good score on my training data and a terrible score on my test data. Of course, it's probably overfit because of that. Let's make a change to that and see if that actually corrects my problem or if I have something else going on that I need to address. And you just keep going through.
So we should always keep track of our RMSE, right?
Which metric you use is, I think, a little bit more about like, what does that metric capture and what do you care about? Root mean squared error is great because it's going to give you your error in the terms of your target. So root mean squared error, if you are dealing in dollars, that root mean squared error can be interpreted in dollars. If I have $140,000 as my root mean squared error, that means I'm on average $140,000 off between what my model predicts and what the actual price is. That metric is not the be all end all, but it is a good one. But maybe I want to do something else, like an R-squared score that's going to understand how much variance in my score am I capturing with my model. R-squared is a really weird metric, but that's basically what it captures, is like how much variance in the scores that I have is my model able to explain. So like that conveys something completely different than root mean squared error. Like it's a completely different metric. And so you can think of, well, let's do both. And then the question becomes, okay, if my root mean squared error gets better, but my R squared score gets worse, do I have a better model now? In the ideal scenario, both of them get better together. But sometimes it happens that one gets better and the one gets worse, or that, you know, the opposite way. And like, you have
Because
to keep playing with
when
it.
R-squared is get lower, the other one is get higher.
Sometimes, not necessarily always. They capture different things. They measure different things. And so because they are metrics that are looking at completely different ways of understanding the results of your model, they don't always go together. And so that's why it's important to look at multiple metrics. I think that only relying on a single metric, although in the grand scheme of things, if that's the only metric you care about, then okay, only look at that metric. But testing, like on your testing data, if you can see multiple metrics, and in scikit-learn, it's just a matter of like another line of code, printing out both. That way you might have a better understanding of like, hey, my root mean squared error, which is an aggregated metric of how far off on average I am, that might get better, but I'm accounting for less variance across all of my points. So maybe I haven't really improved my model as well as I thought I had. And that's why potentially looking at multiple metrics will improve, like, or help you understand like how well you're doing.
The way you're talking about, like, if you use RMSE as your metric, that would entail like repeatedly running your test set against your model, right? Your train versus your test. So aren't you, like, if you do that too many times, aren't you training your test set?
Yep, it's called probing your test set. Yeah, absolutely. But at the same time,
how many times you should do, is there a limit, like how many times you should do that before you made your test set bad?
No, not really. There's no hard and fast rule that I've ever encountered. But if you're really concerned about something like that, do cross-validation. Do cross-validation to understand how well you're doing, because it's not possible to overfit to a test set because you're always using all of your data at some point in your test set.
Sorry, when we did our RMSE, we just calculate the difference between what our model's predicting and our Y trained data set. So every time we calculate our RMSE, it's based off of the training data, and then only the couple, like only at one intermediate point did we check to see if our test RMSE was significantly different than our trained RMSE from our model. So I don't think you don't have to run it on your test set every time you do the model, because that's going to give you just a different RMSE. But then when you find a model that you're satisfied with, then you run it on the test set and see if your RMSE for your testing data is different from your training data, right?
That is absolutely one way to do it. That is perfectly reasonable. I don't know if you were here at the very beginning where I was talking about a holdout set. I kind of use that in my process. And this is one part where like different data scientists are going to have different ways of approaching things and different processes. I typically only evaluate on my test set. Or even better, if I can structure something well enough, I'll only do cross-validation. But at the very beginning of any data science modeling project that I do, I will take a sample of data, depending on like how much data I have. It might be like 5 to 10%, like not necessarily a lot, but I will just like hide it. It's like completely separate, gone from my model's perspective. I'm never going to look at that. And so that way I can make sure that I don't have that poisoned overfit test set problem, where I've basically probed the test set to the point of like not really having it be that distinct from my training data. Like it's learned all of the ins and out patterns of those just as much. And so then what happens is I'll actually probably print out both my training root mean squared error and my testing root mean squared error at every point when I make a change. So I can evaluate that both of them are moving rather than just one. And then at the very end of my process, I'll be like, how'd I do? And throw it against my holdout set and see if I need to go back to the drawing board. But that is something where I think every process is going to be a little bit different. If your process is going through and evaluating on your train set and only ever so often going in to your test set and evaluating, I think that that is completely fine. It is a concern that you are basically learning as much from your test set as you are from your training data, just through the fact of like what decisions you make. These are always going to be problems of the fact that you're trying to pretend you don't know the answers, but you do. Right? If you ever had one of those workbooks where you had all the answers in the back and like you're trying not to look at them, but every time you do, you're like, that's what's happening here. And so the processes that people go through in order to like make sure their model is as generalizable as possible are going to be a little bit different, but it's just a matter of making sure that you're checking. Not only, you're not just training everything on one big set of data and that's the only thing you ever look at. You always need to at some point be evaluating how well you do on a test set, because otherwise you're going to have no idea how generalizable your model is.
That makes sense.
So we've spent a lot of time doing some conceptual stuff, and I do think I have additional questions that are in here. But I do want to talk a little bit about how to actually do some of this stuff. So maybe I'll just share my screen.
I have kind of a question for like everyone. It's more of a poll again. Just if anybody's been playing around with polynomials and interactions and if you've gotten good results from that. So I don't know if anybody has done that at all, but yeah, that's my question.
This quiet group might not have answers for you. In terms of polynomials and different interaction terms, I think one of the interesting things is like that can account for multicollinearity you find in your data. If you find that two columns track the same, well, just put them together and then you've got one column. Like maybe that works better or not. Like you're never going to know until you try. And this is where I think getting into iterations over time of your models, but also like when do you stop? It's a never ending process if you let it be. But yeah, I have here the thread of questions. Doing forwards and backwards stepwise selection of features is not something that's super built into scikit-learn. I've seen very manual ways of doing that. I will try to find a good resource that goes through doing it in code, because I've not found a good way to potentially do this easily. And maybe that's just me not having seen a resource that y'all all have. but I want to say, so Kaggle has courses, free courses that are based on machine learning. And I'm pretty sure I have seen that they have a lesson that talks about doing stepwise selection of features. I may have just made that up, but I'm pretty sure that they have that. And if so, I will share that as a resource. If not, I will find a good blog post that walks through exactly how to do that. And the interpretation just becomes, right? At what point do you trust that your model is learning enough signal and not too much noise? That's in general, like what, it's just a balance of signal and noise of what you can get from columns in your data. But I did want to do k-fold cross-validation. So let's go to sklearn cross-validation. So there's a couple different ways to potentially do this. The hard part with cross-validation, right, is let's say that like you want to have already gone through and done transformations, right? Like you want to go through. And so that's where potentially doing something in a full sklearn pipeline is useful. And that's not necessarily something that we expect at this point in your data science journey. But at any point, you definitely can use this cross-validate to score. And then as we keep going forward, we'll potentially talk about actually building something out into a pipeline. What do I mean by that? Well, a pipeline is just me telling scikit-learn all of the steps that I want to do. And then it's going to do potentially, let's say, 5-fold cross-validation. And at each time that does that train test split, it's going to do all of those steps, including training the transformations, encoding variables and everything. You basically build all of the steps that you do into your pipeline, and then you can make sure that at no point does your model accidentally train on testing data. Scikit-learn does it all for you. It's great, but it sometimes can be a bit of a pain. So I think in terms of like going through and like, because you have to do quite a lot of preparation on some of this data, right? Look at all of these object columns that potentially have, well, date's not a good example, but like, no, this is mostly numeric data. But still, all of your scalars, you should probably do only on your training data. And so you're going to want to scale, all of these variables to be on the same scale before putting them into a linear model. Well, how do you do that when you're doing cross-validation? You have to tell it to do that scaling step and then try to fit a model. And that requires a pipeline. So I think if you're missing the piece of like how to implement k-fold cross-validation, it's probably just because we haven't got to pipelines yet. Does that help answer Mark's question? So Mark, did that help answer your question about like when to run it and how to run it and how to interpret it?
Yep, thanks.
Yeah, when we get to pipelines, that will be super clear. Interpreting dummy variables is tough. Because basically what happens is this is a binary indicator. So let's say I'm going to go through and one-hot encode. I almost always use a different library for one-hot encoding. Scikit-learn has a one-hot encode, right? One-hot encode. Yeah, look at that. Cool. So I'm going to want train test split. Sorry, I am literally this lazy. I potentially could type all of this out, but I never think to. Cool. So let's go ahead and train test split our models. Again, once again, I'm literally this lazy. Cool. Let's see. What is our X? So we've got our data frame. Our Y is price. And then let's do our X as certain columns here. So let's do, just for now, maybe bedrooms, bathrooms, square foot living, and square foot lot. So let's set that as our X for now. You can do as many or as few of these columns as you want, but we'll have, well, here we go. Cool. Sweet. So now I've got an X and a Y. That should be a capital X. There we go. I will go through and do my train test split. And let's look at my data, right? Cool. Have some amount of data. This train test split, okay, yeah, so it's took out 33% as the test size. And we are going through and talking about how to interpret. Oh, I didn't do the one that has, that I would actually turn into a one hot code. So let's actually add zip code. So easy. So now I have my training data and I have the zip code. And so if I want to one hot encode it, encoder is going to be my one hot encoder. And let's see if there's any weird things that I want to do in here. This seems fine. Cool. And we'll encoder dot fit on our X train bracket zip code. Let's see what that returns. It doesn't. Oh, array dot reshape. Scikit-learn is so picky. Am I missing something? Isn't it just reshape? Doesn't like that at all. I didn't import NumPy though, did I? I did. You guys get to watch the probably much more chaotic process of forensic coding stuff. And I'm sure, yeah, there we go. I feel like Ish would be the kind of person who would be like really organized on this. Let's see what this looks like. Oh, and I just spit. Oh, excellent. So what am I doing? I am trying to get the one hot encoded in variables out of this. And if I wanted to, I would get, my encoder is going to have certain features out of it. So I can actually get the name of each of these from here with categories. So I can get encoder.categories. That's all of my zip codes. And so those are basically my columns. So let's actually make this into a data frame and start talking about how we actually interpret this. This is here and columns equals this is someone continue. Alrighty. Well, that didn't work out the way that I'd hoped. Let's see if I can get an example that's actually going to get the name out. Maybe I can just get feature names instead of categories. Otherwise, we'll talk through, let's see if actually this works by itself. Aha, it doesn't like that format one bit. So I would have to unpack that more than I want to. All right, y'all. Live coding on that did not turn out as expected, but let's talk through a little bit about interpreting one hot encoded variables anyway, because we only have a couple of minutes left. Let's say that you go through and you train a model on one hot encoded variables. What does it mean when you have one of them show up as an important feature in your model? Well, what it means is that,
do
what?
Pandas itself has one hot encoding.
The get dummies. Yeah, I could definitely use that instead. Here, if you guys would prefer me having a code example. I think in the grand scheme of things, it is, well, yeah, I could go through and do it that way too. Because I could do, like that. And that would work. So, but I think in the grand scheme of things, right, when we're talking through what it means to have one of these features show up as important in your data, right? How do you interpret that? Well, it's saying out of these 70 different possible options in the zip code, it thinks being in one of these zip codes is really important to determine the sale price, which is a little bit complicated, right? It probably means that it's getting a lot of information about whether or not something is, what the sale price is going to end up being based on whether it's in one zip code. And this is where something like, you know, that's super good for those zip codes, but probably what it means is it's better at predicting some zip codes than others. For this specific example, whenever I have a one hot encoded, and I think someone asked whether or not it matters that these are multicollinear, because of course they're going to have a bit of multicollinearity, right? And the more of these features that you add, you're probably not going to see if you do like a correlation heat map on this. You might not necessarily see. So let's call these zip dummies equals. So if I do an SNS heat map of the correlation on these, I think I can do it like that. I'm not seeing anything because it's almost all zeros. So it's not actually finding any pattern, even though there probably is multicollinearity between these columns, because of course there is, they're all built off of the same column. But you're not necessarily going to see multicollinearity in your data because of it. But I think in terms of like going through, like if I'm seeing that it's better at some zip codes than others, then maybe what that means, or that it thinks that being in a zip code is really important when I go through and train my model, I would really worry about that. I would really worry about what that means, that like deciding that something is not in a certain zip code is like one of the most important things that like you can do to determine the sale price. Like, so that's what happens if you go and like look at feature importance and it has a zip code as one of the things that it thinks is the most important. That's where I would start to think about like, okay, is that useful really? Like that I can predict sale price, like, and it's just based on whether or not you're in the zip code, or is it better to potentially do something different? And what could I do differently? Well, I could take out zip code as a feature entirely, but I could potentially train different models on each of the zip codes and see which ones do better than the overall model, right? Maybe I'm better at predicting some zip codes than others, and those should use the zip code level data as opposed to whole Seattle data. Maybe, and like, is that feasible for this project? Not necessarily, but I think that when you have zip code becoming an important feature, but it's only because of whether or not you're in a zip code, like that's not necessarily useful information to get out, other than there's something weird going on in that zip code specifically. And maybe some other understanding of location is actually going to be more useful if I do something different in this data of like encoding. Someone had mentioned potentially encoding based on like some sense of which zip codes were near each other, getting into a neighborhood level of something. And again, this potentially goes beyond the scope of this project, but could be an interesting way of looking at it.
Can you think of an example where it would be useful? Like you're saying here, you think like if you found these two zip codes are significant, maybe that's not really useful. Is there a case where it would be useful? Like if I was splitting up bathrooms or bedrooms, would that be useful?
Yes. I think when you do something that's a little bit of a different kind of category, you can potentially get a different information out of it. Because, you know, think through what the actual column tells you. The column says this, like each one of these, when I go through and look at this, it says basically, oh, I did paste. Hold on. This column just says, is it in 98001? Yes, no. And so potentially saying, does it have 4 bedrooms? Yes, no. If that is really important, then what it tells you is that a 4-bedroom house versus any other kind of number of bedrooms is really important, potentially as a pro or a con, right? Like you don't know how, like, depending on where the feature selection goes, but like, or feature importance goes, but which, you know, maybe there's a magic number of like 4-bedroom houses are the most popular, or having 2 bathrooms is like the golden number of, you just want 2 bathrooms. That might be a recommendation, right? Like if you can make a change to your house, person who is selling your house, and you can add another bathroom if you only have 1, then that's going to be a really important thing for your price. But feature importance only tells you whether it's important to determining the price. And it will tell you when you, depending on the way you look at it, some of them will tell you how it is important, whether it increases the price or decreases it. And so certainly look at that aspect of it, but potentially like if you can go through and say like, hey, having 4 bedrooms in this house is like really important and like increases the price quite a lot. Like, is that a pattern across all of your categories? Like, does that then become like a line of like only having 1 bedroom subtracts the price, 2 bedrooms does a little bit, and then 3 doesn't really have much of an impact, but 4 is really important, and 5 is even more important. Like, then that becomes a linear relationship between the number of bedrooms and the sale price of your house. That could be really influential. I think the reason why this becomes less useful when you're talking about zip codes is because you can't move your house. Like if you already own the house and you're trying to sell it, like depending on who your target audience is, having zip code as a useful like column, maybe like if that's the only thing that your like, you know, model like really takes from this, like that doesn't help the one person who actually owns a house in this. But if you look at it from a different perspective, right? If your model isn't for someone trying to sell their house, but is looking at people trying to buy houses, then it might tell you, hey, these houses, like, you know, just being in this zip code has a much higher price. And so you could potentially buy a house that's fairly cheap in the zip code, but then like renovate that lot. I'm like, cool. Being in the zip code really highly influences the price. And so if you have a different house on this lot, like then all of a sudden you can probably sell it for more than the same size house somewhere else. That's the only time that I would think zip code would potentially be useful. But that's getting back at your business understanding, right? Like, why are you doing all of this stuff in the first place?
My idea was to, in terms of like get dummies data frame of just bedrooms, if I were to affix a column of price to that and then run a model just on that data frame, would that be comparing them to each other so I could find the important categories?
Yeah, if you went ahead and coded all of your prices, sorry, not prices, all of your bedrooms, and then wanted to see like what that relationship is between bedroom and price, yeah, that you would get at that with like, and what you might find is that it's not as linear of a relationship as you would expect if you just ran a single linear regression between bedroom and price. But it definitely does tell you, right? How much of the price can I predict with just the bedrooms is the question that then you're answering. Sweet. Well, I'm sorry, I have not been working on this project, so I don't have like a bank of code right now on the back end of my computer that I could have just pulled up like, oh, I already have all of this stuff and we can just talk through the code of it specifically. But I have appreciated spending some time with y'all and talking about this project. I love talking about linear models. I think they're really cool and way more useful than, don't forget about linear models when you move into phase 3 and all of a sudden get all of these other cool models too. So, anyone have any last minute questions? I know we're butting up against the end of time. I will find some form of how do we do stepwise regression and feature selection in code. I will find an example for you. Either hopefully that course exists, so I have it in my memory, or I will find a good post that walks through it step by step in terms of implementing it. Because last I checked, unless it's been added into scikit-learn version 22 or 23, then I haven't seen it in scikit-learn. Although scikit-learn adds stuff about every 6 months. So who knows, maybe it's been added and I just haven't seen that they've added it as a new feature in scikit-learn. There's always hope. Other than that, I hope that cleared up any questions that y'all have about like, why a test set, why cross-validation, and what pieces do you do on which stuff in order to have generalizable models. I will wrap up this recording and put it up on YouTube and get it to where you guys can access it. And yeah, I am here if you have any questions today or tomorrow while it's just still out.
Thank you.
Thank you.
You're more than welcome.
Thank you.
Thank you. Thank you.